everyone. My name is Kelly Kane, and I'm the Marketing Manager for EandM. Thank you for attending our Bill Hintz 10 Rules of Diagnostics webinar today. After the webinar this morning, we will be doing a short Q&A. Please type in questions or comments into the Q&A box, the chat box, or email us at eandmwebinar@eandm.com. Now I introduce your presenter for today's webinar, Bill Hintz. Bill has been working with Siemens automation products for 25 years and has many years of hands-on experience analyzing and identifying system failures. Some of his experiences have included a network failure of a dredging barge in the middle of Biscayne Bay in July, a failure during a product launch for a large semiconductor company, a failure for Intel's clean room air shower that ceased all operations. Bill is an EandM Siemens product specialist working with customers to design new applications for Siemens products. Good morning, Bill.
Good morning. Good morning, all, and welcome to our Diagnostics 10 Rules webinar. We're going to kind of focus a little bit today on kind of machine troubleshooting, installations of machinery that's been working and then has failed. Over the years, we get a lot of calls in for tech support issues, and we've done a lot of field service work with down situations, everything from lightning strikes at snowmaking equipment in Tahoe to fixing Presto log plants in Kentucky. But so over the years, we've had quite a bit of experience with this, and this was an opportunity for us to jot down some of the rules that actually make sense, no matter what the industry, no matter what the trade and so forth, but just some outlined rules as best practices for diagnosing and troubleshooting faults in machinery. And having said that, let's go ahead and jump into the first rule. Now, these are not in any specific order, although the first one's pretty important. Let's go ahead and take a look at that, and that is don't panic. The down situation in a plant level environment can be very stressful. You can have a lot of emotions run high, and a lot of people can actually not be at their best at the time. And I remember one time going out on a call to a tomato processing plant up in the Central Valley, and as I got closer, I was on the Highway 80, and for the last half mile before my turnoff, there was just a line of filled semi-trucks full of tomatoes waiting to get processed, and as I pulled onto the frontage road, it was another half mile before I got to the plant. By the time you get there, you see people standing outside of the trucks. There was a suspicious-looking tree over there. I could swear it was going to be somebody with a lynching rope or something. But once you get there, and actually, if you can keep your head about you while all others are losing theirs, then you have an opportunity to actually to do some good. And in this case, it just happened to be that there was a small PLC that was controlling the entry conveyor and doors for the entrance to the plant, which since everything was shut, nothing could get in. And in that case, we were able to just do a couple jumpers to get the doors open and the conveyors running while it gave us time to work on the actual problem, which in that case happened to be some of the old PLCs use battery-backed RAM, so during the off-season, these plants oftentimes shut down and power down. And this one, when they put back up, they hadn't tested it ahead of time, and there was no program in their PLC. So we were luckily able to grab a disk and get them back up and running again. But once again, the idea there just being don't panic. Now, sometimes we get confronted with some pretty tough ones. This is an application which obviously has gone through a series of different Band-Aid and patches, and I can pretty much guarantee you there's no documentation on everything that's been done there. But undocumented repairs, added functions, and Band-Aids and so forth can cause us to, at some point you have to evaluate, does it make more sense to just start from scratch and rebuild this thing, or be another guy in a long line of Band-Aids to get things running? And oftentimes, since it's a down situation in most instances, just getting it running for now seems to be the mission of the day. However, coming back to fix things later on, it's a little more difficult. Anyway, so that's rule number one, don't panic. Rule two, do harm. And what we mean by this, the doctor's Hippocratic oath is actually to do no harm, and that's kind of a moral code, but it can be problematic as well because we can really, if you don't create more problems than exist when you show up to fix something, then you're actually going to have a lot less difficult time finding the problems and causes rather than just fixing symptoms. So don't do anything you can't undo. Good practices are, if you're going to be working on a programmable system, then upload the software application before you do anything to it. So in other words, you can always get back to where you were. Document anything you change before you change it to make sure that you know, if you keep a log of everything you're doing during a troubleshooting exercise, then you don't get to the point where you've actually done a couple of things now that didn't work, and you don't know whether you've introduced new variables into a troubleshooting situation or not. And if, along those lines, if you're not sure why you're changing something, don't. Look for, once again, the causes, not the symptoms. And fixing by replacement of devices is a poor diagnostic method, and it actually can cause more problems, especially if it happens a lot nowadays. A lot of things are programmable. A lot of things have configurations. So just taking a spare part off the shelf and sticking it in and replacing an existing part may just cause more problems. And so last point there, don't fix it if you're not sure what went wrong. That's the same kind of idea there. So, rule number 3, get your tools in a row before you go out to a situation or start working on a machine. That includes all your tools, any toolkits, and you know, if there's any question about what you need and you're driving somewhere, just throw them all in the trunk, and you can always bring them later. But schematics and manuals, laptops, software, cables, all that kind of stuff, make sure you've got everything ready to go. If you keep stopping your process and kind of lose track of where you were to go find something that you don't have with you, I mean, this applies a lot in some applications like clean rooms. I mean, if you have to suit up and go into a clean room to fix something, then going back out and coming back in again is a major problem. Number 4, I always like to talk to the guys in the trenches. And what that means is the guys that are out there working on the machines. You typically be dealing with a couple of different groups of people, and actually filled both roles, either in some kind of a management role or actually in a technician role. So the manager or the production supervisor is going to be standing there with tapping his foot with a clipboards, and when's this going to get running, so he may have a different perspective than the guys that are actually out there working with the machines, and they can be a great resource to just, you know what, yeah, we fix this way every time, but they don't want us doing this, or they, you know, we just felt that maybe we can figure out why this keeps happening and that kind of stuff. The trenches actually do know a lot about the machines, and oftentimes it's more than the people that design them, because they have to work with them every day. So, questions to ask these guys: what happened? Just an explanation of what are you seeing out there? Did the machine ever run? If this is a new install, then we're talking about a completely different ballgame. I mean, new install means that we can have multiple problems. We have to wring out all of the I/O. We have to go through and test every subsystems in a machine and so forth. Whereas typically a failure in a running machine is going to have one cause and hopefully just one symptom, which makes it easier, but oftentimes multiple. Ask them, has it ever happened before? And what would to fix it then? And then let's kind of revisit what, the gained knowledge, the tribal knowledge out there on the plant floors of this country are pretty amazing. Here's a tricky one. What repairs have been made this time? There's always a certain amount of, understandable, it's human nature, a little fear of blame for a down situation. Down situations can be very expensive. You can have a lot of idled labor standing around waiting for the machine to come back up and so forth. So if they tried to fix it, or they were doing something to the machine when it broke, it may be a little hard to get that answer for you. Lastly, just ask them what they think is the problem and basically how they might go about trying to fix it and so forth. Sometimes they can be misleading, but it's oftentimes a very good access point for the knowledge of the working machine. Okay. These rules are not tremendously in order of importance. There's some overall rules. I mean, localize the problem is a very important one. I mean, machinery these days is very complex. It has a lot of subsystems. It can have different functionalities even in the same machine. So localizing the problem actually is a method to eliminate variables and get us down to the actual system that is causing the trouble, rather than if you try to look at an overall machine, oftentimes you can be overwhelmed by the quantity of possibilities and so forth. So when localizing the problem, we want to look at system problems versus local problems. System problems typically seem random. All kinds of different seemingly unrelated problems that can be caused by things like communications and communication going in and out. Noise issues can cause system problems. Oftentimes there's machinery that has high static or electrostatic noise generation capabilities, high frequency noise, arc welders and stuff like that going on and off. Anything like that can cause all kinds of different systems and not consistent symptoms. Wiring is a major one. I mean, I'd say it's certainly more than half of all problems have to do with wiring. Where the rubber meets the road, PLCs and so forth, and I/O cards are typically in a nice environment inside their cabinets. And then if we go out into the real world, out on the machine, we have all kinds of flexibility issues with wiring and flips, smashing stuff, and who knows what else. But loose wiring can be a very difficult troubleshooting exercise, and we'll talk a little bit about intermittence. Non-system local problems are really the ones that we want to find. If we can, back to showing a schematic with all these different subsystems, and actually if we can just zero in on the single part that's causing a problem, we can divide and conquer and actually get into a smaller picture, and it becomes a lot more logical and a lot easier to trace through the issues that led up to a symptom. Okay. And look at number 6 here. Can you reproduce the problem? This is actually the goal of diagnostics, typically, at least an intermediate goal. If you can consistently reproduce the problem or the symptom by toggling it or showing some wires or whatever it is that actually is the cause, then you're well on your way to fixing something. And make it happen over and over again, then it's fairly straightforward to figure out the cause, and we'll talk about cause versus symptoms a lot. If not, then we're in intermittent land. So if you've got one of those machines that you go there to troubleshoot, and you stand there and watch it working for hours on end, and you leave, you get the phone call saying that things have broken again, then intermittent problems are the most difficult to solve, simply because we can't reproduce them typically, and at least not until we found what the cause is. It's simple, but it requires a step, and then some of the tools that we use for fixing intermittence we're going to discuss in a second. And that means going to use our tools. So when diagnosing intermittent problems, we're going to use these tools. So the good old change in light, which the mechanic has the gizmo to take a look and see what's gone wrong in the car, is a good example of what a tool is that can actually give us a look into the past and see what actually caused the problems that we see out there. So let's take a look at example of how we might use those tools. And I'm going to pull in here a programming pack, the TIA portal software for the S7-1200, which I have one online here. And what I'm going to do is simulate an intermittent problem and then show how we can use tools to actually get back in there, look into the past, and be those eyes on the machine that, if this machine only breaks at midnight or something along those lines. And where every time you come back into the plant in the morning, they say it went down again last night, not sure when, not why, but we had to restart it. And the tools we use for that are things like diagnostic logs and online buffers that actually can take a look at the status of the tool on the machine and the PLC and so forth, and log and timestamp everything for us. Now, historically, we've had to write stuff like this. The Siemens products actually have these built in them, so it's automatic to actually see what in the past. And we've got a project open here. I'm going to go jump into it. So this happens to be an S7-1215 CPU. Doesn't really matter. What we've got here is just some real simple code that can generate a fault. And the way it does that is it's going to go out and try to look at the status of an address that doesn't exist. So in other words, I don't have a input word 256 in this PLC application. So as soon as I turn this on, I actually pass power in and create this fault. I've gone ahead and turned it on. We start seeing red lights all over the place. We have an error. So right now, these are the lights on the front of the PLC, and this would be showing a flashing light. So during the instance where this problem is actually happening, we have diagnostics showing up on the PLC, so someone out there on the plant floor could see flashing red light and know that there's an error. However, with intermittents, they just come and go. So now we'll just go ahead and turn that off. Things should sit there for a moment, then refresh itself, and boy, look, everything's nice and green now. What are you talking about? The machine's been running fine. So what do we do in a situation like this? So as I said, this is the instance where we come back in the morning, and we report that the maintenance guy on this midnight shift said there was another down situation. So what do? We go back into our programming environment. We can actually look at something called online diagnostics. And what that's going to do is give us some of the different diagnostic buffers and statuses. So if I look at statuses and so forth, this is all okay. Everything doesn't seem to have any problems right now. Tools exist. Everything's okay. But if I go into my diagnostic buffer, I see down in here that time-stamped about 2 minutes ago, there was a bunch of I/O read access errors that happened in the PLC. Now, this may have been time-stamped in our instance we're talking about at midnight last night. But we can actually see the error. It's got some describing it, or we can go to Help on Event. Click on that. It's going to come up and say, okay, this is the event number, and it says we were attempting to read an I/O address directly, and it failed because a submodule, module, or the device or subsystem has failed temporarily or permanently. Now, that's what we're trying to simulate. In case we actually did it by telling an unused I/O address to go out and take a look at it. But the log would be exactly the same if we had a remote I/O node that failed, or there was power fluctuation that we didn't have power to the I/O module that the PLC was looking at the time. So all those types of intermittents, and this stuff comes up real time into our diagnostic log. So that would allow us to actually see what actually caused the problem that happened last night. So I'm going to close this window. And back here and look in our diagnostic log, and then I'm going to say the Open Editor. What this is going to do is it's actually going to take us to the spot where the problem occurred. And we brought it right up for us. And so this is an example how we use our tools for intermittent faults to actually get us back to the point where we can see what happened when we weren't there to actually see the event itself. Okay. Now, there's some other neat features to this diagnostic buffer is actually available to us in several different forms. Oftentimes, it's local, so we can remotely access this. This is something we can do over the internet if we have access to the PLC. Another way of doing this same thing is to put this diagnostic buffer on the built-in PLC web page, which is fairly straightforward to activate, and then we would have access to the same data we just looked at. The thing is on an HMI device, and if we use if we're doing machine design and designing for diagnostics, then what we're really trying to do is lower the technical requirements for people that are going to be trying to at least be the front line on troubleshooting a machine. So we can actually, in clear language or multiple languages, put up the actual diagnostics in more step-by-step procedure could pop up on a screen saying, go over and check this I/O module, or these wires may be loose, or check the power here, and that kind of thing. So it will actually, as I mentioned, lower the technical requirements of the people that can fix machines. Okay, so minimize that. I get the end of the rule number 7 is that programming software is not just for programming. Oftentimes it will give us diagnostic logs. If the fault is current still, then it's actually going to take us directly to what caused that red light and so forth. So if I had left our intentional fault running, it would actually allow us to just zoom right into to where the problem is. And if in fact we had a machine that had that I/O node, that address that we accessed, causing the fault, if that actually was supposed to exist in the machine, it would actually take us directly to that node as well. So those tools can be very important, especially with intermittents, but oftentimes just with diagnosing wiring faults and so forth. Remember one time we were called out to, actually we did some work with a company that was building a dredging barge, actually rebuilding it over in the East Bay. And it had a PLC on it and distributed I/O, and we were helping them get all set up. And then it sailed off underneath the Golden Gate Bridge, and we hadn't heard about them for a while, but suddenly we got a phone call, and behold, it had gone around and through the Panama Canal and ended up in Biscayne Bay. It was dredged out for the cruise ships, and they had some kind of a penalty contract, and their barge had broken, and they were panicking and so forth. So we actually got called out there and went to see what had happened, and that was an instance where their high pumps that actually, this dredging barge is nothing more than a gigantic backhoe on a dredging barge. So as it pulls stuff off the bottom of the port, it actually just puts it into the barge behind it and does this day in and day out until it's cleared a path. But in this case, the hydraulic pumps were going crazy. First they couldn't get a start, and then once they worked on it for a while, they got it to start, but it was starting at full blast, and it blew a bunch of hydraulic lines, and it was just becoming a big mess. And that's a case where we actually had got there. The documentation was fairly good. However, the environment was pretty cruddy. It was right way down in the bowels of the ship, and there was hydraulic fluid all over the place, and it was kind of yucky and very hot. But in any case, that was an example where the technical guy that had tried to fix that originally went out there and replaced an output module, and actually he zeroed it down to the analog output module that was controlling the speed of the pump, and he saw that it wasn't giving it an output, so he replaced it. In case the do no harm was not being followed, because what happened was he replaced it with a different kind of module. And the module he put in there was, rather than a 0 to 10 volt output, it was a 4 to 20 And those of you that know the difference there, 4 to 20 milliamp modules, when they're off, they actually still put out a voltage. They're trying to maintain a 4 milliamp level, and 4 milliamps is zero. It's off, no pumping. And so when you add that into a system that's expecting a 0 to 10 volt signal, that 4 milliamps sometimes, if it's hooked up to a high impedance input to get 4 milliamps, it's going over 10 volts. So every time they turn this thing on, it was blowing up, and it was kind of a mess. So I was to get them to disconnect their hydraulic pump from the motor, and we were indicating the problem, and we saw every time it came on, even if the PLC wasn't telling it to go fast, it was going full speed. And finally we zeroed in on that module replacement. The real fault was the 0 to 10 volt module had gotten some hydraulic fluid in it. So there was an instance where the fire replace didn't help. And in fact, what should have happened there is that when it didn't work, he should have gone back and put the original module back in place, and it would have made my job a lot easier. In any case, that brings us to rule number 8. And this is an interesting one. It's not always the most complicated part, and in fact, it's oftentimes not. Least understood systems typically are the most often blamed. And oftentimes what that comes down to is if we're talking about programmable logic controllers, then everybody points at that. And so PLCs, their mean time between failure, in other words, how often does the average PLC fail, is measured in decades, as long as you don't have an event. So in other words, as long as there's not been a lightning strike or hydraulic fluid hasn't poured into the PLC and so forth, these things will just run. The code doesn't change. The PLC's hardware is just going to sit there and zoom along. What is typically the problem is something connected to the PLC, and that can be the I/O, which is interfacing with the real world, or the wiring, as I mentioned, which is more than half the time. Sometimes the event problems can, have everybody pointing at the PLC, but network noise and loose wiring symptoms often look unexplainable. I mean, it just went crazy. It never does the same thing twice. It always works when I'm watching. As soon as I walk away, it goes nuts again. Those type of issues, using our tools, actually will allow us to zero in on it. If you try to troubleshoot an intermittent or a system problem by looking at symptoms, you're going to be working for a long time trying to fix this one. Okay, let's talk a little bit about root causes versus symptoms. And here's the analogy here is that the symptom is the weed, and the underlying causes are the roots. And you can pluck that weed as many times you want. It keeps coming back because you haven't fixed the underlying cause. And it's not often obvious. I mean, actually, fixed by replacement is something that's typically done. I mean, we have all heard stories about bad car service places that they just, if you look at the itemized list afterwards, they replaced half a dozen things, and chances are that it was the last one that was the problem, and all these other things got replaced even though they weren't needed. But also, as I mentioned, these can cause other problems too, especially with programmable and configurable devices. I mean, everything down to sensors nowadays have adjustments on them and so forth. Just going out and trying to fix things by replacing them is what looks like the symptom is going to end up giving you a lot more problems than you originally had. And our goal here in diagnostics is to eliminate variables. So we've eliminated all the impossible causes, and whatever's left, that's the solution for you. So critical causes are damaged or loose wiring. Power is oftentimes an issue. Intermittent power supplies nowadays have a neat feature, and if you short them out, they turn off. But if the short goes away, they come back on again. So oftentimes that can be a difficult one to diagnose if you have an intermittent short circuit. So once again, a wiring issue can cause power issues. Part failure. I mean, IO is the most likely. It is actually where it's going out where the rubber meets the road. If you have noise issues, if you have ground issues, if you have electrical discharge issues, then you can blow IO modules. Oftentimes, a lot of the machines that I was out in the field trying to fix were nothing than just an alignment of a sensor. I mean, things mechanically go out of adjustment all the time, so don't forget about those things. I mean, if you're looking at a cylinder extend and come back, check those sensors at the ends. Certainly if a cylinder is all the way extended when you show up and the machine's stuck, then hey, take a look at the extension sensor. Is that on? If it isn't on, then it's probably a good chance that that's what's holding up the machine. Actuators, those are mechanical, electromechanical devices. They can have problems with their coils. For example, if it's a valve or something, or if it's a solenoid valve. It can have problems with a stuck valve. It happens quite often. I mean, dirty air and so forth, you can build up over time, and the actual valve no longer shifts when it's actuated. A big one oftentimes are flow valves and cushion valves. We see this a lot on cylinders. So in other words, flows are actually you see on the back side of the piston. Actually, it allows us to allow the air out of the extension side slowly, so it actually slows down the cylinder movement. Those things can go out of adjustment all the time. If it's all the way off or clogged, then it stops the whole thing. Cushion valves are another. Cushion valves are actually so that when a cylinder gets to the end, it doesn't slam into the very end. It actually is just a little valve that actually gives it air compression and is supposed to bleed off and just slows down the thing at the end. That can oftentimes have a big problem with sensor alignment. So oftentimes if a cushion valve is stuck and not allowing full extension any longer, we may not be making our sensor alignment for that reason. If that's the case, moving the sensor is going to be a short-term Band-Aid fix, but it's that cushion valve that is the cause. Mechanical jams, they happen all the time, and oftentimes people will blame the control system when it is actually just a bunch of cardboard stuck in a sleeve or something that is not allowing the machine to function. Last on this is if you can point to what you caused the problem, it's probably not fixed. And oftentimes this happens, and you're working on a machine, and then mysteriously it starts working again, and you're not sure exactly what it was that you did to fix that. Tell this, but the chances are pretty good that you haven't fixed anything. It's just it's an intermittent or temporary problem that comes and goes, and probably will be back. Okay. Rule number 10. Man, everything. This is important. I mean, we saw back there on our first slides about don't panic with that awful control cabinet. There's documentation on that thing, I'll guarantee you. It's to document everything we did. We're going to make it a lot easier for the next guy that comes along, which may be you. You may be called back out to work on something. So document everything. Software, any changes you made, version numbers that you saw when you got there, any differences between the software that the guy handed you and what you saw inside the machine itself. Those can be issues that can come back up and bite you later. If you've changed any wiring, make sure those schematics get updated. So people that come in next are actually looking at drawings that are actually true representations of what that machine is. Manuals. If there are parts of the manual that you used, notate it. Put a little sticky on there and make sure that people are, and you can jot down in your procedure log. Oftentimes also in every machine has its own little log book in it, and that is a very good place to put down anything you did and just to help out the next guy or yourself or me or whoever's doing it next. The procedure log is real important. So if you can actually show your steps and your thinking as you went through diagnostics and troubleshooting on a machine, jot down, keep a log of it, then next guy that comes along yourself, if you're back in there with the same issue again, you can actually see what you tried, what did work, what didn't work, and all the other things that actually might be able to help out next time, including improvements to the machine. You can put recommendations in there as well, and certainly you want to change things in a down situation, but recommendations for updates or changes that might help this machine work better and so forth are also good things to jot down. Okay, I see a couple of questions have come in. First of all, Bill, how are you feeling? Well, thank you for your, for the question. Actually, those of you that were on this last time, I woke up with no voice the last time we scheduled this. So thanks for asking. I'm fine now, thanks. Boy, it was weird. I guess sometimes you can just completely lose your voice. All I was doing and squeaking and popping and not making much sense. It would have made a difficult or interesting webinar. Another question. Why would you use 4 to 20 over 0 to 10 analog? And actually, there is a lot of 0 to 10 out there. Boy, 99% of the time I'd prefer to see 4 to 20. 4 to 20 milliamps as opposed to 0 to 10 volts is just a better industrial design signal. First of all, with 0 to 10 volt, 0 is a valid number. So if you break a wire and you're at the end actuator and you're measuring a voltage out there, 0 volts, you don't know whether the wire's broken or it's actually just sending a 0 signal. 4 to 20, and I mentioned this on that barge that we dealt with, the 4 milliamps is the 0, the off, simply because now if it goes below 4 milliamps, then we know there is a wiring issue. We know that there's a wire break or some other fault that's causing that signal to go below what should be its minimum of 4 milliamps. And then milliamps are better is that it's in a single path loop, an output back to a return signal. You the same current level throughout that circuit as long as there's not multiple paths in it. What that means is that we don't care so much about voltage drops and so forth. 0 to 10 volts, you could have 9 volts coming out of the PLC and 8.5 showing up at the actuator because of the resistance of the wiring. 420 milliamp within reason will compensate for resistance in wiring, and so that when you send out 4 milliamps at the PLC, that's 4 milliamps that shows up at the actuator. And diagnostics-wise, we can actually turn on things like wire break detection and so forth, so we actually do know if there's a wire break or if it actually can't achieve its 4 or milliamp signal levels. It'll tell us that as well. 0 to 10 is kind of open-ended. It just, 0 to 10 appears at the PLC and away it goes. Okay. There are suggestions here for some rules and so forth. I think that's great, and certainly we'll be reviewing this. This is a living document. This is kind of the first time we jotted all these thoughts down at one time. But let's talk a little bit about what they are. Once again, it's don't panic, do no harm, get all your ducks in a row, your documentation and tools and so forth. Talk to this in the trenches. That's who I find to be the most helpful. Localize the problem. Try to get away from looking at the machine as a single entity and take it down to the subsystems that typically make up tools. Like there's oftentimes motion control and temperature control and valve gas flow and other different subsystems of a machine that actually, if we can focus in on those, it helps us out quite a bit on just, it gives us a lot less variables to deal with. problem. If you can reproduce the problem, you can probably fix the problem. Use your tools. Certainly with intermittence, we need to be able to look into and see what that check engine light means. Remember, it's not always the most complicated part, even though a lot of people will say that it's that crazy controller again. Treat the cause, not the symptom. I should probably move that up very close to the top. Document everything. We also do a lot of work with machine design for diagnostics, and there are a lot of tools available to us to actually, when we're doing the design phase. So those of you that work on machine design, we'd talk to you about it, because there are a lot of options out today with diagnostics and so forth. And I think it's one of the underutilized features that a lot of the Siemens PLCs have. I mean, we can actually just checking the box turns on all kinds of diagnostics that, I don't see many people checking those boxes. So I'd love to talk to you about that or any other machine design issues and so forth. If you have any more questions, always call our toll-free number or send an email to our sales@EandM.com. Appreciate your time today, and happy Friday, y'all.
Great, thank you. And if anyone would like to review any portion of this webinar, a recording will be available on our website, EandM.com, by Monday afternoon. Also, the next webinar is scheduled for December 13th. It's 7-1200 Modbus TCP. And if you have any other questions after this webinar, feel free to email us at EandM@EandM.com. And thank you, everyone, for attending.